Hey friends, welcome to follow up. Let's have a look at a new problem, problem 2831. Find the longest equal subarray. And in this video, we're going to explain a solution based on two-pointer sliding window trick again. So here we are given a zero-indexed integer array called nums and an integer key. So a subarray is called equal if all of its elements are equal. So note that the empty subarray is an equal subarray. So here we want to find the length of the longest possible equal subarray after deleting at most key elements from nums. So this is our main task. So here a subarray is a contiguous, possibly empty sequence of elements with an array. So here are two examples. In the first example, the output is 3. So actually we can have this one, right? From this one, if we delete 2 and 1, we have 3 threes, right? So the length is 3. So in the second example, so we have 4 ones, and we can delete the 2 twos here, and then we get 1 1 1 1, right? The length is 4. So here the constraints are the following. First, the length can be as long as 10 to the power 5, which is a decent large number, right? So nums I is bounded below by 1, and it's actually less than or equal to the length of the nums list. So the k is also in this bound, but the k can be 0, right? So for this problem, actually the hint is very suggestive, but we can follow the hint. So here, basically for each number, unique number x in nums, we create a list. The list will store the indices where this x appears, and then over each for each unique element, we can consider the corresponding indices list, and then we do a two-pointer sliding window method. So basically, this is the main condition, right? So if this condition holds, then we have this number of equal elements, so we can return the maximized such formats. That's the hint 4. So here we want to do some more analysis. So for example 1, so if we look at the 3, so the corresponding indices is 1 3 5, and the index or indices list for each unique number, so let's call this index A. It has a property that is AI is greater than or equal to I, because I is the index here. So for 0, at index 0 this is 1, and 0 1 is 3, and 0 2 at index 2 this is 5. In other words, the index in the original array is larger than the index in the index array. So this is very natural to understand, right? So basically, if we use two-pointer sliding window for the list of the array A, right? So what we want to do, so for each index G, or we can see the right pointer, so we find the smallest I such that this condition holds, and then we have this number of equal elements, that is J minus I plus 1, right? So actually this condition holds. Actually, we can digest like this. So we can digest this formula. So then at index I we have AI, right? At index G we have AG, right? So because we are considering the indices for the index list for a unique element, so from I to G, right? So G minus I plus 1 is the number of the number of appearances for this unique element. For example, 3. So if we look at the index 0 and the index 2, it appears 3 times for this one. And then what's the AI? So AI will be the index for this occurrence at the original array. So here AG minus AI plus 1 will be the full the length of the subarray or the segment in the original list, right? So then if we use this number, so we use this AI, AJ minus AI plus 1. So we use this number minus J minus I plus 1. So this is nothing but the elements we would like to delete, right, in the original list or in the corresponding segment in the original list, starting from index AI, ending at index AG, right? So this is the number of the unique number in the corresponding segment. So then, because this 1 and 1 cancels, so we get this condition, right? As long as the number of other elements deleted is less than or equal to k, so we see we have such number of same element or equal element. So this is what we want to digest. Another thing is that due to this property, so for each right index g, right? So if this condition holds, let's see, for each g we have a corresponding leftmost I, right? And then if we increase g, then this leftmost I should remain or increase, right? So in other words, we have the monotonicity for two-pointer sliding window method. If G1 is greater than or equal greater than G2, in other words, G1 is in the, let's say G2 is greater than G1, so G2 is the one step further. So what it implies is the corresponding I2 is no less than, so in other words, greater than or equal to I1. So the reason is very easy to digest. For example, if we increase I by 1, so this is increased by 1, but AI is increased larger. So this, if J is fixed and I is increased, so this overall, so will be small, right? So with that said, we are ready to look at the code. So basically, if you do not, you couldn't digest this two parts, this formula and this part, you can look at the code and print out the information to get a better understanding. As for coding, it's actually very straightforward. So let's write with some redundancy so that we get a good idea. So first, we want to find the indices list for each unique number, unique elements. So this is actually very simple. So we can use say collections default dict. So we can put the container to be a list, and then we just need to iterate, right, for y in enumerate. So nums, and then we just for this unique element y, so we are going to append the corresponding indices. So here the property, as we mentioned, for each dy. So this is the list. You can see, call it a, right, as here. So you can digest ai will greater than or equal to I. This is the property, right? So then what we want to do, we do two pointers, right? Two pointer sliding window. So this is the very routine. So in order to so here our goal is to find what we want to do is we can write a function. Let's say call this function given an array. The array will be the indices list for a unique element. So for this, we want to find the longest equal subarray. So for this, let's first initialize a result. So because let's assume it at least 1, right? Because as long as this array is not empty, the result is at least 1. And then let's first have the left pointer, that is 0. And then for each right pointer for I in range length array. So we want to find the corresponding leftmost left pointer L, and then we want to check the condition that on this range we can do deletions, so that we can have such number of equal unique number. So basically this is the while loop. While L is less than R, and the condition is array R minus array L, then minus R minus L, if this is less than K, right? And then so here let's write in another direction. If it's greater than K, so we want to increment L by 1, right? So because if this is larger, we want to make it smaller, so we can like here we want to increase I. So if you increase I is increased, let's see, by 1, but AI is incremented by at least 1, right, due to this property. Then it moves towards smaller, right? So that's why we have this L plus L incremented by 1. So this basically is a proof of correctness. So then after we exit this while loop, so basically there are two possibilities. Either is L equals R, or this condition validates. In other words, this formula is less than or equal to K, right? So if it's the latter, so what we are going to do is to update the result, right? So we have L R minus L plus 1 equal elements, right? And then we can just compare with the result. So another case is L equals R, right? But this condition does not hold. In that case, when L equals R, this is 0, right? They still give him 1, so it's like doing nothing. So, but it can be unified as this condition. So this always works. And then after we got each comparison for each right index, we just need to return the result state. So this is the hyperfunction. So next we are going to prepare the return. So this is very routine, right? So let's so notice the scope, right? Here result is a local variable within this function. So we can still use this result as a variable name. And then for array, we are only interested in the array. We are not interested in the unique number here. So in the values, right? And then what we want to do, we get the corresponding result. So for this list, that is F array, right? And then we update the result, that is max result in the F array, right? And then what we want to do, we want to return the result. So this actually forms a solution format to this problem. So before we make any comments, let's first do a test. Yeah, it passes the first example. So now let's look at the generic case. Yeah, it passes all the generic cases. So that's basically about it for this specific problem. Here some comment is the following. First, I guess it's important to realize the monotonicity of the order relation, which actually enables us to use the two-pointer sliding window more effectively. In other words, if we scan the right pointer to the right, and then we don't need to start over the left pointer I or L in our specific function here. So then this is the one comment. Another comment is that this is just one format of writing the solution to this problem. And for example, here you can, for this hyperfunction, you can consider the difference. For example, here we have 1, 3. It means that in between there's one index 2, right? So here we can actually transform this problem. If we consider the difference sequence, so we can find a longest subarray with sum less than or equal to K, right? So for example, from 1 to 3, so this 2, we need to delete 1 right? From 3 to 5, we need to delete another one. So its total is 2, right? So that list is 2. Then we are going to have 3, right? So this is then this find the longest subarray with sum less than or equal to key. This is also a very standard problem which can be solved using two-pointer sliding window method, but in another format compared to the two-pointer sliding window method we use here. I guess for this problem, the hard part might be digest the formula or digest the monotonicity. So otherwise, the coding part is rather straightforward. So with that said, I guess that's about it for this video. Thank you.